sometimes useful to do. For example, M for CO2, air and water. M for CO2 dividing between air and water is about 1,500 at room temperature and pressure. If I change the pressure, I can drop M down. So if I increase P, M goes down. If I double P, M is 750. Things are becoming more soluble, at least when I'm looking at this in terms of mole fractions or mass fractions. So this is a bunch of, yeah, there's a lot of notation that has to be gotten under control. So this is some of it. I guess I might have a remark that as M goes up, solubility goes down. In fact, there's another thing that is sometimes written we might use. You might write this as P equals H prime X. 1 over H prime people call the solubility. So you can relate H prime to H, you can relate H prime to M, and so we're sitting here with H, M, H prime, but they're all equivalent. They can all be derived from H, and so that's how we start. We start with a little background information. Now we say, okay, we got a column here. Let's pretend like maybe we are trying to strip ammonia out of water by blowing air through. So here I am. Here's my column. This is a point Z in my column. I am going to work in terms of Y being a flow average mole fraction, X being a flow average mole fraction, because I don't really want to take transverse effects into account. Besides, the mixing's pretty good transversely. And besides, I want to make mass balances with these X's and Y's, so they better be flow averages. So here I have this coming up at a flow rate V, and this going down at a flow rate L. And I might say to myself, V dy dz. Why does Y change? Y changes with X because solute is moving from that phase into this one. So I need to say that Y, V dy dz has to do with the rate at which I'm adding solute to that phase. Rate of adding solute.
Wait, what did you say the difference between V and Y is? What is the difference between V and Y?
V and Y are like always. We've never changed our notation. V is a flow rate, Y is a mole fraction.
V is a flow rate.
Okay, inconsistent units. This is also equal to L dx dz. So, if I'm going to account for changes in this composition and that composition, I have to have a model for the transport from that phase to this phase. So let's introduce some notation. And the way you do that is exactly the way you did it in heat transfer. You introduce some mass transfer coefficients now instead of heat transfer coefficients. So I will do this. I will say this is, I will say that if I want to calculate the rate of mass transfer there, I'll introduce a mass transfer coefficient ky. And I will write this as yi minus y. We'll get to what this is in a minute. But I'll also introduce a mass transfer coefficient kx, which is x minus xi. So locally in the column, so this is at some z. write this. And of course, my dimensions of ky and kx for that matter are going to be dimensions of mass per time per length squared. So here's what I think I see somewhere in a column. I think I see a bulk phase on the y side, a bulk phase on the x side. Maybe here is, I don't want this to look. Okay, here is roughly an x composition, and then there's an interfacial composition xi, and then if there's little interfacial pieces here, there might be interfacial composition yi, and there might be a composition y in this phase. So I might have prevailing at some z, an average concentration y of this phase flowing up, an average concentration x of this phase flowing down, and some equilibrium pair xi, yi at the interface. So it's a common assumption to assume that everywhere you, oh, this is what you did in heat transfer. You assume the temperatures at the wall, well, the temperature in the various phases were equal to the temperature at the wall when you were at the wall. So what are we going to say about xi and yi? We're going to say xi and yi are an equilibrium pair. So if we have an equilibrium diagram here, which gives y equal to mx, then anytime you think you have an xi, the yi is right there, so that's the point xi, yi. So if xi changes through the column, yi changes through the column, and of course xi does change through the column, and so does yi. But we can begin to write down a model for doing something with this much information. So here's what we would write to begin. We would go d dy dz equals ky. How do I want this to look? Y I minus y. And now I need an area contact. So I'm going to introduce something called A, where A is the area of surface per unit volume of the column. And so I'll put a cap A in here, so that cap A dz is the element of volume. So if you were to multiply A dz, you would have the amount of area in this little slice right here between z and z plus dz. So you got some area in here of contact. That's this. I have no idea what little a is. The hope is that it goes into all the other crap that I have no idea about. And of course it does. So I write that, but I notice that the yi, well, it's looking pretty good so far. Here's a y, but there's a yi. So let's continue what we're doing and observe this is also kx, x minus xi, a, and observe that this is also same equals same. So now I've got two equations sitting here. Depends on how you want to count things. Involving y, involving x, involving interfacial compositions. They're related by the factor m, and also have a mass balance floating around. So the mass balance, if I make it around the top of the column, down through a certain point where I'm working, as we have done in the past, I would say y v, which is an input, I guess, plus x in L. That's an in, that's an in, so it must be y out v plus xl. If I know what's going on at the ends, this is the material balance. This relates y and x. yi and xi are related by yi equals mx. And I might struggle through this if I wished. But that's not the way it's done. Here's the way it's done. To get rid of xi and yi before we go on, to get rid of xi and yi before I solve these equations, what you do is you do exactly what you do in heat transfer. You never really wanted the wall temperature to be carried along in your calculations. And so what you do is you define something called cap AX times x minus x star, and you define something called cap KY, y star minus y. Now, what I'd really like to do is, well, y star is defined to be mx. Y is defined to be mx star. So this is the definition of y star. This is the definition of x star. We can put them on our graph. So if we're at a place where this is the x, this is the xi, this is the x star, then this point right here would be x and y star, and this point right here would be x star and y. All these 3 points are on the equilibrium line. They're all different ways of talking about equilibrium. The advantage of this one is that y star depends only on x. The advantage of this one is that x star depends only on y. So if I put in for my stuff up there, y star minus y times a cap ky, or an x minus x star times a cap kx, which I'm certainly going to do, I will have something that looks more doable. I will have cap ky, y star minus y, aa. I could also write cap kx, x minus x star, a, like so. Same. Now what's nice about this, if I choose to use this, is the y star is mx. If I choose to use this, x star is y divided by m. In either case, you don't see any yi's, you see only the x's and y's that were appearing in the balance equations to start with. So I've now reduced this thing to a problem in x and y. However, kx and ky are the fundamental mass transfer coefficients, and they are going to have to tell me what cap ky is and what cap kx is. So let's do that argument. You've probably seen it before. Let's see what we have here. I have, let's start with this one. Cap ky, star minus y equals ky times yi minus y. What I've got to do here is eliminate this yi, get y star in its place, and change this ky to cap ky. This is one of your favorite moves. So here's the plan. We will go to ky yi minus y equals, and what I'll do here is I'll write this kx over m, and then I'll write mx mx is y star. Good. Y star minus yi. So all I did was took this, divided that by m, put m in here, observed that mxi is yi, mx is y star, I get this. Now I solve for yi. Solve for yi. Well, it's clear that yi is going to equal, well, I'm going to get a kx y star over m plus a ky times y divided by, okay, looks like it'll be divided by kx over m plus ky. So I'm going to take this yi that I just solved for in terms of y star, going to shove it into here, collect terms, and when I do that, I'm going to come to find out that 1 over ky is 1 over little ky plus m over kx. So kx and ky, little kx and little ky give cap ky. And I can do this again and come to find out, again, same moves. I could come to find out that 1 over cap kx is equal to 1 over mky plus 1 over kx. Then I would look at this and say, well, okay, little kx and little ky give me the two cap k's. Are the two cap k's independent? Well, no. Now we'll find out that m times cap ky equals cap kx. So they're not independent. Yeah, that's right. Okay, so now I'm ready to make some progress. I'm going to put all this crap together in there, write the cap ky and or the cap kx, and write my model down, and if I need to use this, I will. So let us make a choice at this point. So we've already made one choice. Our first choice was units. I'm choosing to work in mole fractions and so on. I did not choose at this point to work in partial pressures. My second choice will be to work with the transport on the y side. So my second choice will be to work with those equations. So, and this y star, of course, is mx, so I'm looking for differences mx minus y. This also is mx, so I'm looking for differences mx minus y. So I'm going to arrange this. Now, we're just going to do the heat transfer. We're going to make all the heat transfer moves. So we say to ourselves, I want to take those two equations, and whenever I can, I would like to reduce them to one equation, if I can. Make one equation out of this. So what I'm going to do is I'm going to multiply this by m and divide by m. So I'm going to have something like v dy dz, and down here I'm going to have L over m dmx dz, and both of these hand sides are the same.